This is part 1 of exercise hollow plate in chapter 2. In this exercise, we'll set up the model and run the first study. So open the model hollow plate. This is a part model. And let's make sure first that simulation is added on the list of add-ins. So go to Settings, Add-ins, and make sure that SOLIDWORKS Simulation is added on both sides as active add-in and startup add-in. Done. Then make sure that we have Command Manager enabled. So I have Command Manager here. This is the space where different commands will be showing. Right now I have Simulation Study tab already selected. But of course, using Command Manager, you can move through all kinds of tabs here, features, sketch, mesh modeling, and so on and so forth. So let's stay in simulation. Before we create a new study, notice that material is not specified yet, meaning that material has not been assigned to car model. We'll assign material to simulation model in this exercise. Alright, so if you select Simulation tab in the Command Manager, you should see this New Study buttons. Click on it, and so from the list of different types of studies, select the default static one, static, and name it Tensile Load. Tensile Load 1. So now we are in simulation, not in CAD, but in SOLIDWORKS Simulation. And you can see that Tensile Load 1 tab has been added right here. So now you can, if you need to, you can switch between model and simulation simply by selecting different tabs along the bottom of the screen. Let's have a look at the menu here. So Tensile Load 1 is the name of the study. Next one, hollow plate, refers to the model being analyzed. And you can see two symbols here. One with curvy cube, meaning that SOLIDWORKS Simulation has identified the geometry as candidate for meshing with solid elements. And the next one, to the right, is blue tetrahedron with kind of curvy edges, indicating that once we mesh it, we'll be using solid tetrahedral second-order elements. We have some other connections. We'll not be using connections here, fixtures, external loads, and mesh. Now we could go ahead and proceed with analysis, but for convenience, we'll have a look and modify some simulation options. So go to Simulation, Options, right here, and go to Default Options. In Default Options, make sure that units are SI, length is in millimeters, and pressure or stress is in newtons per millimeter square, meaning megapascals. Then, in Mesh, make sure that this measure type is standard. So select standard. We'll be using standard measure in many exercises in this book. Pay attention to one thing, that if you select standard, if you change from blended, for example, blended curvature mesh to standard, this change will take effect only after you reload the simulation. So we'll check the measure type one more time in this exercise. And finally, another option that we want to modify is location of results. So save results to a different folder than SOLIDWORKS document folder. In my case, I'm saving results to FEA results folder in root directory of D drive. it's much more convenient to keep model separate from result database. It's not absolute requirement, but it's much more convenient. All right. So now we are ready to apply material. So right-click on hollow plate, apply edit material, and the default material is alloy steel here, showing in this material window, and this is exactly what we want. So select apply and close. Now, as a confirmation that material has been applied, you can see green check mark has been added to this cube symbol. We don't have to define any connections, so we can skip this, but we have to define fixtures or supports. So right-click on it, select fixed geometry, and rotate the model so that you can see the other end of the plate, and select this narrow end face and define it as fixed geometry. Click OK button and proceed to definition of loads. So right click on external loads, select force, select the opposite face to where support has been defined, and we want to define the force magnitude as 100,000 newtons. 100,000 newtons. Tensile loads, so also select reverse direction. Now model is ready for discretization, called meshing. Right-click on mesh, select create mesh, and in mesh parameters, one more time, verify that we are using standard mesh. Using standard mesh is much more convenient in the convergence process. Our convergence process will start with coarse mesh, so move this slider all the way to the left. And here in mesh parameters, we can see that we'll be using elements with global size 11.45 millimeters. Alright, so click OK button and mesh will be created. So this is coarse mesh created using second order solid tetrahedral elements. We are now ready to solve it. So right click on tensile load 1, study name, and go to run. The solution is almost instantaneous, and you can see that 3 plots have been added to the results folder, and the active plot is shown using bold font. So right now we are looking at stress 1 plot showing von Miser stress. We can look at displacement. We can look at strain. Let's start with displacement. We'll make some modifications to this plot. So right click on displacement 1 in the results folder, and let's select first settings. In settings, we'll change fringes to discrete. Discrete fringes are easier to analyze. In chart options, we'll modify numerical format of results. So rather than using scientific, we'll be using floating format with as many as 6 decimal places. Why so many? Because we'll need this many decimal places to see the difference in displacement results as we continue with the convergence process. Normally, of course, we wouldn't use as many decimal places for displacement results. Alright, in stress 1 plot, so first activated, we see von Miser stresses. And those are nodal stresses. Nodal stresses, meaning that stress results are extrapolated to nodes and then averaged on nodes among different elements. So let's do some housekeeping. We'll call it, this plot, von Mises nodal. Von Mises nodal. Alright? Let's make some cosmetic changes to this plot. So in chart options, once again, we'll use floating, and we don't need too many decimal places. 2 decimal places will be plenty. In settings, we'll use again discrete fringes with superimposed mesh. It's always a good idea to have a look at results with superimposed mesh. So here it is, this modified plot. Finally, what we can do is we can also create von Mises stress element. So we can either create this stress plot from scratch, or we can copy this von Mises nodal into a new plot and modify it. It will be much faster, so you can click on it, drag it and drop it into results folder. So this one we will activate now. Alright, and again using click inside technique, we'll rename it into von Mises element. Of course, nothing has changed yet. We have to edit plot definition. So right click on it, and selection between nodal element stress is done in edit definition. So in those advanced options, let's select element values. Here, now you can see right away that nodal stress plot shows maximum stress 340 megapascals, and stresses are kind of evenly changing over elements. In von Mises element, maximum stress is only 310, and each element has one unique stress value. We'll talk about it later when we analyze results. You can also move the location of plot, so you can arrange it so that we have first displacements, then von Mises nodal, von Mises element, stress. One more plot that we can add is factor of safety plot. So factor of safety plot definition consists of 3 steps. First, in step number 1, we have to decide what definition of factor of safety are we using. We can leave it on automatic, but to make it more visible and clear to understand, we'll do the selection manually. So we want to base factor of safety on von Mises stress. The factor of safety is defined as maximum von Mises stress divided by yield strength. Okay, in step number 2, we don't want to use any multiplication factor, so we set stress limit to yield strength, and yield strength is 620 megapascals. You can verifying by looking up material properties. And in step number 3, we want to see areas below the factor of safety, let's say 3. Okay. Here it is. So everything shown in red color is below the factor of safety 3. And again, factor of safety is related to von Mises stress. Why to von Mises stress? Because alloy steel is ductile material, and we use von Mises stress to calculate the factor of safety. So this completes almost tensile load number 1 analysis. We can do one more thing here. We can select any plot and animate it. So displacement plot, select animate, and you can see model deforming. Scale of deformation is 169.76. So of course it's exaggerated. And the exaggerated scale of deformation is used so that we can observe model deformation more easily. So we have set up the model, we have created mesh. We analyzed briefly results using coarse mesh. This will be first step in our convergence process. We'll proceed in part number 2.